Okay, well, how's everybody today? Great. Good, good, good. So, what we got going on, the plan for today is we're going to go ahead and start by talking about any questions you might have on that assignment I gave you. I believe it was the Thursday before Thanksgiving break. And after that, we'll go ahead and continue talking about polar graphs. That'll continue through the rest of the week. But tomorrow, we do have that quiz over polar coordinates. So you want to make sure you feel comfortable plotting a polar point. Can you convert from a rectangular to a polar, polar to rectangular, that type of thing. And there'll also be some complex problems on there. Remember that Thursday, I believe we were talking about points in the complex plane, A plus BI. So all of that will be on that quiz tomorrow. Don't forget that Thursday morning at 8:05, that's the deadline if anybody wants to retake that equations quiz from before the break. Oh, and next Thursday, the 11th, we have our second exam of the 9 weeks. So we're going to be really close to wrapping this up. I mean, we've only got a little over 2 weeks left, and we're already done. Questions? Okay, well, let's take a look at the homework here. So the front of it's going to look like this. It'll say Worksheet A, 3.13. Okay. What questions do we have? Hey, 23? 23. Okay, so 23, air traffic control system is tracking 2 fighter jets, both of which are flying at the same altitude, and their directed distance is measured in kilometers. If they have coordinates of 4, 150 degrees, and 2, 195 degrees, find the distance between the 2 jets. Okay, so the only thing about this is just being able to recall that formula. It was rather large. Okay, let's go ahead and say that this is my first radius, theta 1, second radius, theta 2. We're going to get a little more room here. Okay, let's see if we can go ahead and remember this. So the distance was going to be the first radius squared plus what was that? The second radius what? Squared. And I'm going to subtract 2 times what? Theta. The first radius times the second radius times sine or cosine. Very close. Cosine of theta 2 minus theta 1, and then all of that was below the radical. So there was our formula. Okay. Now, this formula will work whether you're given degrees or radians. I would encourage us to work in radians. That way we don't even have to change the mode. You got everything you need. So let's go ahead and take the difference. 195 minus 150. What's that going to give me? 45 degrees, and that's really easy to work with. That's pi over 4 radians. Now, we could have changed 195 and 150 to radians and subtracted them, but it's just way faster to do it that way. Okay, so let's go ahead and plug in. The distance is going to be the first radius squared, so 4 squared, plus the second radius squared, 2 squared, minus 2 times 4 times 2 times the cosine of that difference that we just found to be pi over 4. Okay. And all of this was below the square root. Now remember one thing about cosine, was it an even or an odd function? Close. Even, okay? So remember, even means this. Let me go ahead and write this out. So if I were to have cosine of negative theta, that just means cosine of theta. Remember, that negative on my variable simply disappears. So if you happen to have subtracted this, the 150 minus 195 and gotten a negative, that wouldn't have changed anything. You still would have been able to get the right answer. Okay, so at this point, let's just go ahead and plug in what we've got. So we got 4 squared plus 2 squared. So I'm going to go ahead and start with the square root of 20. Okay, 16 plus 4. Then it would be minus 2 times 4 times 2 times the cosine of pi over 4. All right. And I mean, you can simplify more of it if you want to. I mean, you can just type it in exactly as you have it on your paper. That doesn't make any difference. But when I push enter, looks like we have 2.95 kilometers between the two jets. 2.95 kilometers. All right. Mariana, is that good, man? Okay. What else? Well, you'll definitely be converting. Do we want to do like one polar to rectangular and a rectangular to a polar? Okay. Okay. Let's see here. What are some questions that the other classes asked? There was one in particular. 15 has been a common one. Okay, let's look at 15. Okay, so 15 says the location of point A in rectangular coordinates is a negative 1/2 square root of 3 over 2. Which of the following describes the location of point A in polar coordinates r theta? Now here's what's really nice about these types of problems, especially when they show up on the AP exam. This is the only way polar anything is going to show up on the AP exam. It has to be part of the multiple choice section. Now, whether it's part of the calculator or the non-calculator, we won't know for sure. But use the answers to your advantage. Okay? It is really, really helpful. Sometimes it can get you straight to the answer. Sometimes it might just eliminate several answers and give you a better shot. Okay? Now, if we're going to do it by hand, if I wanted to go from rectangular to polar, I'd want to use these two formulas. I'd find the radius by taking the square root of x squared plus y squared. And then I'd use tangent of theta is equal to y over x to find my angle. So those are the two formulas I would use if I'm going from rectangular to polar. But before we even get started, let's see if I can eliminate some answers. This negative 1/2 root 3 over 2, what quadrant would it be in? Negative x, positive y. So that'd be quadrant 2. So whatever point or answer I choose has to be in the exact same quadrant. Well, let's start with A. Pi over 3 with a radius of 1, that's in quadrant 1, so that's automatically eliminated. Okay. B, 5 pi over 6 with a radius of 1, that's a possibility. C, 2 pi over 3 with a radius of 1, that's also in quadrant 2. What about D, though? That's in quadrant 3. So I wasn't able to get down to the final answer, but at least I eliminated 2 potential answers. Is everybody okay? All right. Well, let's go ahead and find the radius first. Okay, so this is going to be the radius equals, so x squared, negative 1/2 squared, plus y squared, square root of 3 over 2 squared, all below the radical. Okay, so what is a negative 1/2 squared? 1 over 4 plus square root of 3 over 2 squared? 3 over 4. So that would give me 4/4, so it looks like I'm getting the square root of 1, so my radius is 1. So that was easy enough to find. Unfortunately, it doesn't help me out with the 2 answers I have left. So at least we know the radius is 1. Okay, we kind of already knew that. All right, so now we got to go ahead and find the angle theta. That's what's going to help me find my answer. So tangent of theta equals y over x. First thing I need, though, is y divided by x. So let's see here. The y value is a square root of 3 over 2 divided by a negative 1/2. Now we're dividing by a fraction. What's that mean? We're going to multiply by the reciprocal. Okay, so let's see here. Square root of 3 over 2 times a negative 2 over 1. See, the 2 and the negative 2 are going to cancel, so it looks like I'm getting a negative root 3. Okay. Now remember, we got to use the inverse to go ahead and find that angle. So here's what I'm working with. Tangent inverse of that negative square root of 3 has got to give me theta. Okay. So let's see here. Quadrant 1 or quadrant 4? Four. Why? Because it's negative. Okay. So I'm going to go ahead and draw a triangle here in quadrant 4. I'm going to go ahead and make that over 1, so we have a fraction. Y divided by x, so this would be a negative root 3. That's a 1. If I use the Pythagorean theorem, I should get that hypotenuse as 2. So this is a 30, 60, 90 triangle. And what's this angle right here? It has to be 60. Remember, 30, the smallest angle, has to be opposite the shortest side. Okay, so what I'm finding here is that theta is going to be a negative 60 degrees. Remember, we had to rotate clockwise, so it's negative. So a negative pi over 3 is my angle. What's the problem? Yeah, see, here's the thing. We're working in quadrant 4. We already said this point is in quadrant 2. Okay, so what we did to fix this before the break, let's take the hypotenuse of this triangle that I drew. Let's just extend it into the quadrant it needs to be. That's always going to work like that. Okay. Now, by extending this hypotenuse, I created vertical angles. So if this is 60, this is also 60 right here. Now remember, in order to get to this line that I just created, you have to rotate again from standard position. So how far do I rotate to get 60? 120. It's a horrible 20, but there you go. 120, there you go. But 120 degrees is 2 pi over 3. Okay. So if I'm going from rectangular to polar, here are my 2 equations that I'm going to use. So now let's go ahead and do one where it's polar to rectangular. So another popular one today has been number 12. Let's take a look at that one. So number 12 here, the location of point X in the polar coordinate r theta is negative 4 pi over 3. Which of the following describes the location of point X in the rectangular coordinate xy? Okay. Now, if you're going to go from polar to rectangular, here are your 2 formulas, r cosine of theta and y equals r sine of theta. But let's see if we can eliminate some answers before we even go ahead and plug those in. Okay. Negative 4 pi over 3. What quadrant is that in? It is in quadrant 3. Well, wait a minute. Pi over 3 is in quadrant 1. What am I forgetting? Remember, what happens with a negative radius? There you go. It doesn't go towards your angle. It goes in the opposite direction. So even though, yeah, pi over 3 is in the first quadrant, we're not going towards it. We're going to end up in quadrant 3. So I'm looking for a point that's also in quadrant 3. Okay. Well, let's see. X and Y are positive. That's quadrant 1. That's already eliminated. Same thing for B. X and Y are negative, so that's a possibility. Where is D? Ooh. That's quadrant 4. So just by knowing the location, I was already able to get that answer. That won't happen every time, but it's definitely worth a look. Okay. Now, let's say you didn't realize that. Let's go ahead and plug one of these in. Okay. Let's say I do want to go ahead and evaluate the radius is negative 4 times the cosine of the pi over 3 that we got. Okay, so I'm going to go ahead and draw the angle pi over 3. Okay. I'm going to use that to create a right triangle. And remember, I'm always going to default back to the unit circle. We're going to say the radius is 1. What was across from 60? Root 3 over 2. And across from 30 was 1/2. So the cosine of pi over 3, that's a 1/2. Negative 4 times 1/2, see, there's your negative 2. And if I were to go ahead and simplify negative 4 sine of pi over 3, I should be getting negative 2 root 3 as well. All right. Anything else? Like I said, basically, if you know how to plot a point, if you can go from polar to rectangular, rectangular to polar, and you feel comfortable with the complex plane, should be an easy quiz for you tomorrow. Doesn't take me a lot of time at all. Anything else? Okay. Did anybody have that ready to turn in? Okay. Okay. All right. Well, let me go back and set this up for the next class. Ooh, there we go. Okay. Let's go ahead and take a look at our notes from yesterday. Right. Okay. So we're looking at how to graph these polar functions. Okay. So we started off yesterday with some basic equations. If you're only given the radius, we found that that was going to be a circle centered at the pole. Okay, everybody seemed to do pretty well with that. If you're only given theta, then we end up with a straight line. Okay. And then we started to get a little more complex. Our first one was 2 sine of theta. Now, the one thing about this, I went ahead and provided you this reference sheet yesterday to go ahead and help you out. So we were really focusing on that first column yesterday. A cosine of theta and a sine of theta. We're going to recognize these as circles. Okay. Remember that leading coefficient A, that was the diameter of the circle. If it was cosine, you're going to find it along the x-axis, because it's the x variable. If it was sine, you're going to find it along the what? The y-axis, because it's the y variable. Okay, and then you choose the appropriate location, whether A is positive or negative. Like, for example, if you're dealing with cosine, a positive A is to the right of the pole, a negative A would be to the left of the pole. Now, again, I'm going to emphasize this, especially when we start going further with this today. The more of this you have memorized, the easier things will be on you. Okay, that's just a guarantee. You're going to be able to find certain answers immediately without doing any work. Okay, but here's the thing: you don't have to have this memorized. I know a lot of students are not going to have that, and that's okay. There's nothing wrong with that. We're going to be looking at different strategies so that even if you don't have this committed to memory, you can still get what we're looking for. Like in this case here, a table is going to be really helpful to you. Okay, so we were looking at 2 tables in increments of pi over 6, so 30 degrees. One of the characteristics of the table, in the first part here, whatever you got for a radius length, what happens to that length in the second part of the table? It becomes the opposite. So if you've already got the first half filled out, you already have the second half filled out. Okay, so plotting points is a great way to go ahead and work these. Now, yesterday, we finished up with number 9. Okay. Now, what we found was that if we're graphing cosecant in a polar plane, we ended up with a horizontal line. In fact, this one was a horizontal line, y equals 1. That is right there. Okay. Now, we want to go ahead and use this idea to kind of help us predict what's going to happen in other problems. If graphing cosecant in this plane gives me a horizontal, what's graphing secant in the same plane going to give me? What do you think? Cosecant gave me a horizontal line, so secant's going to give me a vertical line. Now, I just mentioned the table. We're wanting to graph 1/2 secant of theta. So remember on one page in your packet, I went ahead and gave you all these blank tables for you to use with these problems. Okay? They're there if you need them. But you'll notice, just to help save us some time, I've got 1/2 secant of theta, that table filled out. Okay? Like, for example, if I go ahead and plug in 0, 1/2 secant of 0, I got 1/2. 1/2 secant of pi over 6, I got square root of 3 over 3. And the same characteristics are going to apply. Whatever radius length I got in the first half, it becomes the opposite in the second half. Okay? And remember, for these, especially if you're looking at tangent, cotangent, secant, cosecant, those have asymptotes. So it's not unlikely that you could end up with a no solution when you try to plug in a particular angle. Okay, so let me go ahead and give you a second to jot that down. And then we'll go ahead and plot this and see what we end up with. We're looking at a lot of patterns today. And you'll notice down here at the bottom, I've already approximated the square root of 3 divided by 3 is about a 0.58. But you actually have the calculators today, so you can check that if you want. Okay, so if cosecant is going to give me a horizontal line, then I should expect secant to give me a vertical line. Well, let's go ahead and start to plot these. So at 0 radians, I've got a radius of 1/2. Now, be careful here. Again, every 2 circles, that's 1 unit. So 1/2 would be right there. Okay, in fact, let me go ahead and make that a little bigger. There we go. So there would be 0, 1, or 1/2, 0, I should say. Now let's go ahead and plug in the square root of 3 over 3 pi over 6. And we know that this approximation is a 0.58. So at pi over 6, we're just going to go slightly past that 1/2 mark right there. Okay. And then at pi over 3, I've got 1. Okay, so that would be right here, the second circle. We didn't get anything at pi over 2. 2 pi over 3 gave me -1. What happens with a negative radius again? I'm not going to go towards 2 pi over 3. I'm going to what? I'm going to go in the opposite direction. So I would have this one right here. Okay, and you'll notice it's not perfect, but the more points you place, you are going to notice that a straight line is forming. Right there. So we did end up with a vertical line. Now, just like I did yesterday with number 9, let me show you on number 10 why you get a vertical line. Okay, so let's start with the reciprocal cosine. So we know that cosine of theta gives me x over r, right? Okay. Somebody do me a favor, solve that for r. What would r equal? So cosine of theta equals x over r. I want r equals. Drake? Oh, no, we're not taking the inverse. We're just manipulating the equation. So it would be x over cosine of theta. Did anybody want me to show the middle step? Okay. So we're going to use substitution here. If I know that the radius is equal to x over cosine of theta, let's plug that back in the original equation. So instead of r equals, I'm now going to have x over cosine of theta equals 1/2 secant of theta. Excuse me. All right. And let's say I want to go ahead and just have it x equals. So I want to get rid of that cosine. So I'm going to go ahead and multiply through by cosine. Well, cosine divided by cosine, they're going to cancel. There's my x equals. Now, remember your identities. What's cosine times secant? What happens if I multiply reciprocals? I get 1. So 1/2 times 1, that's just 1/2. See, I ended up with the vertical line, x equals 1/2. In fact, are you noticing a pattern here? Like I wanted to graph 1/2 secant, and I ended up with x equals 1/2. Okay, that scale factor became the value for my vertical line. Look at this in number 9. Okay. Graphing cosecant, I got the horizontal line y equals 1. What am I multiplying cosecant by? 1. That scale factor in front, that's going to determine whether you're horizontal or vertical line, where it's going to be. Okay, so let's kind of put this into practice. Let's come on down here. Okay, let me get this out of the way. So on number 11 right here, sure, I could go ahead and rewrite it as rectangular like I just did for number 10. I could go ahead and create a table of values like we've previously done, but should cosecant give me a vertical or a horizontal? Should give me a horizontal. Okay. Where do you think that horizontal line is going to be? Y equals what? -2. Well, remember, here's 0, so let's go down 2. That would be right here. There you go. Pretty cool, right, Noah? Awesome. So see, if you realize these characteristics, these patterns, it can save you so much time. Like, what if I were to go ahead and give you the radius equals -2 secant of theta? What graph would I get out of that? Remember, secant, is that going to be vertical or horizontal? Vertical, so it's going to be x equals what? -2. But again, you run through a table, all that stuff, you're still going to end up with the same thing. Think of the table as your safety net. Even if everything else fails, if you forget, you can still create a table. Okay? It'll take a little more time, but you'll still be able to get to what you need to. All right. Let's go ahead and put it to the side. Let's look at this guy right here. Okay? So I want to go ahead and introduce you to limesons. That's how you pronounce it, limesons. It comes from the Latin word for snail. If you actually start looking into the history of who developed these ideas, it's actually pretty fascinating. But anyways, limesons and roses. Okay, so we're in the second column right now. So limesons, they're going to be of this form: a plus or minus b cosine of theta, a plus or minus b sine of theta. Now here's the one thing: both a and b have to be positive. You're always going to look at a and b as positive values. So there's some good news here. You remember how cosine and sine, when we were looking at circles, if it was cosine, it was along the x-axis, sine was along the y-axis. The exact same thing is going to apply here. Yes? Did you misplay? Did you have it yesterday? Okay. Why didn't you say anything? What? Okay, there you go. All right. So what are the 4 types of limesons that we can have? All right, so we have a limeson with an inner loop. That's pretty self-explanatory, so it kind of loops in on itself. Okay. We have a cardioid. This comes to a specific point when you push in part of the circle. Kind of think of a cardioid as a fat heart. Okay. We have a dimpled limeson. Imagine just kind of pushing the circle inside, not where it comes to a point, but where it still has a smooth curve to it. That's considered a dimpled. And then convex, I did not do a very good job here when I went ahead and sketched this. Convex, one part of your circle is going to be flat. So kind of think about it like this. You ever played with Play-Doh? Sure, everybody's played with Play-Doh, right? You ever made a ball with Play-Doh? If you went ahead and put it on a flat surface, what happens to that part of the sphere that hits this flat surface? It flattens out, right? So imagine if you picked up that Play-Doh ball with that flat surface there and you were looking at just a cross section of it. So it looks like a circle where one part of it's flattened. That's what it means to be convex. Okay. Well, how did these two forms give me these different graphs here? Well, it's the ratio of A to B and how they compare to other numbers. A is always the first number. So if A divided by B is less than 1, you've got an inner loop. If A divided by B equals 1, you've got a cardioid. If A over B is between 1 and 2, it's a dimple. And if A over B is greater than or equal to 2, you got yourself a convex. So I've given you an example of each one of these. Okay. Now, I want to go ahead and stress, like for example, 1 plus 2 cosine of theta, that is not that exact graph that's right there. You're going to get a graph that's similar to it. Okay, so I'm not saying that's the equation of the graph you have. So we're okay with that? Okay? But let me ask you a question. 1 plus 2 cosine of theta, what's A? A is 1. What's B? B is 2. It always goes in order. A is first and B is second. B is what you're multiplying against the trig function. Okay? Now, what would you say about the cardioid? 2 minus 2 sine of theta. What's A? 2, what's B? Ah, okay, that's where some people get kind of tripped up. B would also be 2. If it's being subtracted, you don't want to look at that as a negative. Think of it as a reflection. Okay? Because remember, whether it's sine or cosine, it's got to be on one part of that axis. Okay? So let me go ahead and start showing you how to put these in the calculator, because this is going to be super useful to you. Let's start with that first one. 1 plus 2 cosine of theta. All right. Everybody got a calculator? Okay. So let me go ahead and get rid of this. Okay. All right. So I like to use the scratch pad for graphing. You can do the same thing for a document. Again, just please clear the calculator's memory, before you bring it back. So here, right now, it's rectangular. So I have to tell the calculator that I'm putting in a polar equation. So I'm going to go to Menu. I want to go to Graph Entry Edit. And then I'm going to choose number 5, polar. Okay. So let me go ahead and escape out of this again. Okay. So if I want a polar, I'm going to go to Menu, Graph Entry Edit, Polar. And you'll notice the radius equals. I can put in my function. Now, if you look down below here, this gives you your interval and what kind of radian measures they're going to put in. So what do you think? What does 6.28 represent? That's 2 pi, right? So one interval, this is 1 full revolution right here. They're going to graph this for us. Okay. Now, when it says theta step, those are the increments of radians that we're going to put in. So it's going to start by substituting in 0.13 radians. Then it's going to put in 0.26 radians. Then 0.39 radians. So it's going to do it in that increment. That's probably the one thing you won't ever have to change. Okay. So let's go ahead and type in what we have here. What was it? 1 plus 2 cosine of theta. So 1 plus 2. Go to my trig button over here, cosine. Now you have to use theta because that's what they're using in their descriptions down here. So at the very bottom left of your calculator, that same button we use for pi, if you click it, theta is one of the characters. Okay. So I'm going to go ahead and click enter. There we go. So there's my inner loop Limason. Okay. Now remember what I said, A is 1 and B is 2. If it's cosine, you're going to find it along the x-axis. If it's sine, you're going to find it along the y-axis. But let's go back in here real quick. Let me change one thing. Let me go back up here. Let's say all I do is change it from a 1 plus to a 1 minus. What do you think it's going to do to that graph? Will it still be along the x-axis, or is it going to change to y? It's still going to be along the x, but what's going to happen to it? There you go. There you go. And you can sit here and play with this. I've got given you some of these other ones. Let me go ahead and show you another one of these. Let me document B out of here. Let's plug in the convex one, because that's not a very good one that I drew. So the one I have here is 6 plus 3 sine of theta. Okay, 6 plus 3 sine of theta. So I'm going to come back over here. So I go to Menu, Graph Entry Edit, Polar. So 6 plus 3. This time I want sine of theta. Remember, I'm going to use this pi button down here at the bottom. Okay. Now, should I expect this graph to be more on the y-axis or the x-axis? Definitely on the y because it's sine, but should it be above or below? Should be further above. Not to say that a portion of it couldn't be below, but the majority will be above. Let's see. There you go. And see, this is what I was talking about. You see how the bottom of this is just kind of flattened? It's just this one little section here that's kind of straight. That's what a convex limacon is. Okay. All right. And then if I did the same thing, if I were to go ahead, go back in here, if I change that plus to a minus, it's still going to be along the y-axis, but it's going to flip it. Okay. All right, so those are limacons. Okay, so don't think of it as a negative b. It's a reflection with B. Does that make sense? Okay. All right, well, let me go ahead and clear this out. And then these are the ones that I really like to show you. Okay. Roses. These are where you can start getting some really spectacular graphs. Okay. So here's the form, A cosine of n theta, A sine of n theta, where n has to be greater than or equal to 2. So you know you're going to be dealing with the rows because you're multiplying your variable by some number. Okay. So the leading scale factor A, that's going to be the length of one of your petals. Okay. But let's see if you folks can pick up on a pattern here. What is that there? There we go. Okay. So let's say I have A cosine of 3 theta. Well, you'll notice I'm multiplying theta by 3. So how many petals do I have? I got 3. A sine of 2 theta, but I've got 4 petals. A sine of 5 theta, I've got 5 petals. But A cosine of 4 theta, I've got 8 petals. What am I trying to get you to see here? What determines the number of petals? Whether it's odd or even. If you multiply theta by an odd number, that odd number is the number of petals you're going to have. But if you multiply it by an even number, you double that. That's the number of petals you're going to have. Now, it's a little more difficult to talk about symmetry here. So whether it's sine or cosine, I mean, it could be symmetric with the x-axis, with the y-axis, or even both. So we won't worry about symmetry when it comes to the roses. Okay. But let's go ahead and plug in a few. Let's see what we got. So I'll come on over here. Okay. How do I get to polar again? Menu. Okay. Graph entry edit. Polar. Okay. So what do we want the length of each of our petals to be? 6. Okay. All right. And it doesn't matter sine or cosine. What would you like? Sine. Okay. Let's plug in sine. Now, what do you want? I hope I'm not being set up for something. What would you like me to multiply theta by? 3. Okay, there we go. Got a little nervous there for a second. I thought someone might have said a particular number. Not that anybody knows what I'm talking about, right? Yeah, okay. All right. So each petal is going to be 6 units long. But how many petals should I have? Should have 3. So let's see. Okay. So let's go ahead. Let's go back into tab. Plug this back in. Oh, what the heck? I've already done it. 6, 7. Okay. So I have 7 petals. Okay. You knew it was coming. Okay. All right. Let me go back into tab. Let's put in an even number this time. What would you like me to put in? 4? So if I put in 4, how many petals should I have? 8. Each 6 units long. Okay. And this can get pretty awesome. If I go ahead, go back into here. Oops. Oh, I got you. Oh, thank you. Let's go back. Hello. Oh, I didn't do it for second period. Okay. Thank you. Okay, so let's put in something like, let's put in, how about 12? So how many petals should I have? Okay, 24. Remember, if it's even, you double the number. If it's odd, then it stays the same. So see, you can start getting some pretty pictures here. You know, to kind of play around with it, see what you got. Do 56. Okay. Don't know how the resolution will hold up on that, but let's see. Okay, so what's 56 doubled? 112. So there you go. That got crazy. Wow. And you know what's really cool? Let me go back over here. Only one class has asked me about this so far. Like, what happens if you put in a decimal? Like if I go ahead and plug in 5.5, you'll start to get an overlap. Yeah. So, I mean, it's really cool if you sit here and play with this. I mean, you can get a lot of really nice pictures. But are there any questions about roses, James? Oh, yes, 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 yes. Now, we won't be doing that, though. We're just doing like the basics of polar graphs and equations. Uh, Basically, for what you're going to be doing in calculus, if you know how to convert and plot a point, you're already ready to go. But the fact that you're going to be able to recognize some of these graphs, you're already going to be ahead of the game. Okay. All right. Well, let's come on back over here. So, unfortunately for the other classes, I didn't get to a problem where we actually started working one of these today, but were there any questions on either of those? Was there anything that was confusing somebody? Has anybody decided they're going to commit this to memory? Okay. You don't have to. I got strategies that are going to help you out. Okay. But so with that, we are done for today. So please remember to clear your calculator's memory. Let's go ahead and get those up to the front. And I'm going to shut this down.